April 2020 semester ICT 6900 Special Topics in ICT Advanced Machine Learning কোর্সের lecture 2তে সবাইকে স্বাগত জানাচ্ছি। Today's topic is linear regression one variable and some fundamentals of linear algebra. Our first learning algorithm will be linear regression. In this lecture, we'll discuss what the model looks like and more importantly, what the overall process of supervised learning is. Let us use a motivating example of predicting housing prices. We are going to use a dataset of housing prices from a city and then we'll plot the dataset of a number of houses. Let us say that you have a friend who is trying to sell a house and say your friend's house is of size 1250 square feet and you want to tell him how much they might be able to sell the house. One thing you could do is fit a straight line to this data. Then based on that, you could tell your friend that his house could be sold at around 240 lakhs of tag. So this is an example of supervised learning algorithm. And it is supervised learning because we are given the right answer for each of our examples. Moreover, it is a regression problem where the term regression refers to the fact that we are predicting a real valued output, the price. And then just to remind you the other type of supervising learning problem, which is called the classification problem, where we predict discrete valued outputs, such as if you are looking at cancer tumors and trying to decide whether a tumor is malignant or benign, so there is a 0 or 1 value. More formally, in supervised learning, we have a dataset, and this dataset is called a training set. And for a housing price example, we have a training set of different housing prices. And our job is to learn from this data how to predict the prices of the houses. Let us define some notation that we are using throughout this course. I am going to define a lot of symbols. If you do not remember all the symbols right now, no problem. But as the course progresses, you will learn all notations gradually. So I am going to use lowercase m to denote the training example. For example, if you have 47 number of training examples, then m will be equal to 47. Let me use lowercase x to denote the input variables. This x, this column, is the input variables, or sometimes it is called features. Rather, it is called input features. And I am going to use y to denote output variable or target variable. The second column is your output variables. I am going to use x comma y to denote single training example. So a single row in the table corresponds to a single training example. And to refer to a specific training example, the superscript I over here is used. That means the I over the superscript I x superscript within bracket I and y superscript within bracket I is a specific example, ith training example. I is the index to training set. So xi, yi, the superscript I in the parenthesis, that's just an index into my training set. And it refers to the ith row in the table. So if we write x1, then actually x1 refers to input variable for the first training example, x1. In this table, x1 is equal to 2104, the first row, first column. Similarly, x2 would be 1416 y1 will be 460. If you see the table, x1 is 2104, x2 is 1416, and y1 is 460. And that's the first y value for my training example, and so on. So for a specific element or specific row, we use superscript. So here is how a supervised learning works. We have our training set of housing prices and we feed that to our learning algorithm. The job of a learning algorithm is to then produce a function, which by convention is usually denoted by lowercase h. H stands for hypothesis. And the job of the hypothesis is to find a function that takes the input the size of a house, then the size of a new house that your friend is trying to sell, it takes in the value of x, and h is a function that maps x to y, where y is the estimated price. Some of you know the meaning of the term hypothesis. People often ask why this function name is hypothesis. Whatever it turns out that in machine learning this is the name and was used in the early days of machine learning. But the term hypothesis maybe is not the best possible name for this, but this is the standard terminology that people using here. In the next slide, I am going to choose our initial choice for representing the hypothesis. The following is how to represent h. H equals to theta 0 plus theta 1 of x. And as a shorthand, sometimes y is a linear function of x. So there is a data set, and what this function is doing is just predicting that y is some straight line function of x. And we will build on this to eventually have more complex models in more complex learning algorithms. So this particular model is called linear regression with one variable or univariant. So that's the linear regression. In the next slide, we'll start talking about how to go about implementing this model. Now we'll define something called the cost function. This will let us figure out how to fit the best possible straight line to our data in linear regression. We have a training set like that shown in the slide. Remember our notation m. M was the number of training example, and so it may be m equal to 47. And the form of our hypothesis, which we use to make prediction, is this linear function. To introduce a little bit more terminology, these theta 0 and theta 1, what we call the parameters of the model. And what we are going to do in this lecture is talk about how to go about choosing these two parameters values, theta 0 and theta 1. With different choices of parameters theta 0 and theta 1, we get different hypotheses. Just as a review, here are a few examples. If theta 0 equals 1.5 and theta 1 equals 0, then the hypothesis function will look like this. And because your hypothesis function will be h of x equals 1.5 plus 0 times x, which is this constant value function. If theta 0 equals 0 and theta 1 equals 0.5, then the hypothesis will look like this. And finally, if theta 0 is equal to 1 and theta 1 equals 0.5, then we end up with a hypothesis that look like this one. In linear regression, we have a training set like the one which is plotted here. What you want to do is to come up with values for the parameters theta 0 and theta 1. This corresponds to a straight line that somehow fits the data, maybe that line over there. But the question is, how do you come up with theta 0 and theta 1 that corresponds to a good fit to the data? The idea is we are going to choose our parameters theta 0 and theta 1 so that h of x meaning the value we predict is at least close to the value y for our training example. Let us formalize this in linear regression. What we are going to do is to solve a minimization problem. So write minimize over theta 0 and theta 1. We want the difference between h of x and y to be small. And one thing I might do is to try to minimize the square difference between the output of my hypothesis and the actual price of a house. We take a square of the differences or error because the error could be positive and negative. If we take direct sum of the errors, they may cancel out from each other. So what we want really is to sum over my training set, take sum from I equals to 1 to m of the square difference between the prediction of my hypothesis and the actual price. I'm going to actually look at 1 over m times the summation. So we'll try to minimize the average. In fact, minimize 1 over 2m. 1 over 2 in front just makes some of the math bit easier. So this is going to be my overall objective function. Therefore, the cost function for linear regression is the one shown. There are other cost functions as well that also works pretty well. But the square error cost function is probably the most common used one for regression problem. In the next couple of slides, we'll go a bit deeper into what the cost function is and trying to give you better intuition about what it is computing and why we want to use it. In the previous slide, we gave a mathematical definition of the cost function. In this slide, let's look at some examples to get better intuition about what the cost function is doing and why we want to use it. To recap that we had last time, we want to fit a straight line to our data. So we had this form of hypothesis with these parameters theta 0 and theta 1. And with different choices of the parameters, we end up with different straight line fits to the data, and that is a cost function, and that was our optimization objective. So I'm going to use my simplified hypothesis, which is just theta 1 times x. If you want to think of this as setting the parameter theta 0 equal to 0, so I have only one parameter theta 1. And my cost function is similar to before, except now h of x, that is now equal to just theta 1 times x, and I have only one parameter theta 1. So my optimization objective is to minimize j with respect to theta 1. What this means is that if theta 0 equals to 0, that corresponds to choosing only hypothesis function that passes through the origin that pass through the point 0, 0. And for this hypothesis, we want to minimize the cost function. Using the simplified definition of hypothesis and cost function, let us try to understand the cost function concept better. It turns out the two key functions we want to understand. The first is the hypothesis function and the second is the cost function. Notice that the hypothesis h of x for a fixed value of theta 1 is a function of x. And in contrast, the cost function j, that is function of the parameter theta 1, which controls the slope of the straight line. Let's plot these functions and try to understand them better. Let's start with the hypothesis on the left. Let's say here is my training set with 3 points 1, 1, 2, 2 and 3, 3. Let us pick a value of theta 1 and let's set theta 1 equal to 1. And if that is my choice for the theta 1, then my hypothesis is going to look like this. And I want to point out when I am plotting my hypothesis function, now I have temporarily set theta 1 equal to 1, which I want to do is figure out what is the j of theta 1 when theta 1 equals to 1. So let's go ahead and compute what the cost function is for the value of theta 1. As usual, my cost function defined as follows. In every case, h of x and y are same. So the difference between the hx and y is always 0. So that is why I find that j of 1 is equal to 0, and the green colored dot represents that value of j theta 1 when theta 1 is equal to 1. What if theta 1 is equal to 0.5? What happens then? Let's go ahead and plot that. I'm now going to set theta 1 equals 0.5, and in that case my hypothesis now looks like this line with a slope equal to zero point 0.5. And in that case my hypothesis now looks like this as a line with a slope equals to zero point 0.5. J of 0.5 is about 0.58. Let's go and plot that. The green dot is 0.58 at a value of theta 1 equal to 0.5. Now let us do one more. How about if theta 1 is equal to 0? And what is j of 0? It turns out that if theta 1 is equal to 0, then h of x is just equal to the flat line. You end up with a value of j around 2.3. And of course, we can keep on doing this for other values of theta 1. So in the plot, you see on the right hand side, the j of theta is equal to 2.3 for theta 1 equal to 0. If theta 1 is minus 0.5, so that corresponds to a hypothesis with a slope of minus 0.5. And you can actually keep on computing these errors, and it works out to be something like 5.25 is the value of j, and so on. You can actually slowly trace out what this function of j theta looks like, and this is the plot of j with respect to theta. Now you remember the optimization objective for our learning algorithm. We want to choose the value of theta 1 that minimizes j of theta 1. This was our objective function for linear regression. Look at this curve. The value minimizes j of theta 1 is theta 1 equal to 1. Just for the particular training set, we actually end up fitting it perfectly. And that is why minimizing j of theta 1 corresponds to a value where theta 1 equal to 1. And to wrap up, in this part of lecture, we looked at some plots to understand the cost function, and to do so, we simplify the algorithm so that it had only one parameter theta 1, and we set the parameters theta 0 to 0. In the next slide, we'll go back to the original problem and look at some visualization involving both theta 0 and theta 1, that is, without setting theta 0 to 0. And hopefully that would give you an even better sense of what the cost function j is doing in the original linear regression formulation. Let us develop deeper and even better intuition about what the cost function is doing. This lecture assumes that you are familiar with contour plots. If you are not familiar with contour plots or contour figures, some of the illustration in this lecture may not make sense to you. But it's okay, and you will still understand the rest of this course without those part of it. Here is our problem formulation, as usual, with the hypothesis parameters, cost function, and our optimization objective. Unlike the last slides, I am going to keep both of the parameters theta 0 and theta 1 as we generate our visualization for the cost function. So same as last time, we want to understand the hypothesis H and the cost function J. So here is my training set of housing prices, and let us make some hypotheses. Although the one shown in the slide is not particularly good hypothesis, but if I set theta 0 equals 50 and theta 1 equal 0.06, then I end up with this hypothesis down here. And that corresponds to that straight line for the given values of theta 0 and theta 1. We want to plot the corresponding cost function on the right. What we did last time is we only had theta 1, but now we have two parameters, theta 0 and theta 1, and so the plot gets a little bit complicated. When you plot theta 0 and theta 1 in x and y axis in that three-dimensional plot, the z-axis is the value of j. This is shown in the right side of the slide. The plot we drew in the last slides was a sort of bowl-shaped function. Now when we have two parameters, it turns out the cost function is also a similar sort of bowl shape. And in fact, depending on your training set, you might get a cost function that may look like something that is shown in the slide. So this is a 3D surface plot where the axes are labeled theta 0 and theta 1, and as you vary theta 0 and theta 1 as two parameters, you get different values of cost function j of theta 0, theta 1. And the height of the surface, that is the vertical axis, or the height of the surface at a particular point indicates the value of j. And you can see it is a sort of bowl-like shape, but I am going to use contour plot or what I call contour figures in the next slide. Here is an example of contour figure shown on the right, but the axes are theta 0 and theta 1, and each of these ellipses shows a set of points that take the same value for j. For example, these 3 points have the same value for j, and these points shown in the figure has the same j value. If you have not seen contour plot before, follow this discussion now. Say you have a bowl-shaped function as shown in the slide. The minimum point is at the bottom of the bowl. The concentric circles above the minimum point are of same j value because each of the circles has the same height above xy plane, that is theta 0, theta 1 plane. On the right hand side, the ellipsis corresponds to the concentric circle on the left hand side. The left hand side shows the three-dimensional plot, and right hand side is the contour plot. It is the equivalent two-dimensional plot corresponding to the three-dimensional plot on the left. And so the contour figures may be a more convenient way to visualize the function j. So let us look at some examples. I have a particular hypothesis shown in the slide. This is with theta 0 equals 800 and theta 1 equals minus 0.09. And so the point in the red in the contour diagram corresponds to one pair of values of theta 0 and theta 1. This hypothesis h of x with these values of theta 0 and theta 1 is not a good fit to the data, and so you find that the cost as a value is there. Let us see the red point is pretty far from the minimum point, which is shown by the arrow mark. Let us look at some more examples. Here is a different hypothesis that is still not a good fit of the data. It may be slightly better than before. So here the theta 0 value is about 360 and the value for theta 1 is equal to 0. And this pair of parameter corresponds to a flat line. That is, h of x equals 360 plus 0 times of x. So that is my hypothesis. And this hypothesis again has some cost. You can see the point on the contour plot is not close to the minimum point. It is still far from the minimum point. Since the straight line, that means the hypothesis, is not a good fit. That's why cost is not minimum. And the minimum cost point is shown again by the arrow mark. So let us see another example. There is one more. At this value of theta 0 and that value of theta 1, we end up with this hypothesis h of x, and again not a good fit to the data. This is not such a bad fit to the data, where for a particular value of theta 0 and theta 1, we get a particular h of x, and this is not quite at the minimum, but is pretty close. And so the sum of squares error or sum square distances between my training example and my hypothesis, that is the sum of square distances of all of these errors. So with this example, I hope that this give you a better understanding of what value of the cost function j are and how they correspond to different hypotheses, as well as how better hypotheses may correspond to points that closer to the minimum of the cost function j. Now, of course, what we really want is an efficient algorithm for automatically finding the value of theta 0 and theta 1 that minimizes the cost function j. What we do not want to do is to try manually. We do not do that. That is not a good way to do it. When you look at more complicated examples, we'll have higher dimensional figures with more parameters, where the figure cannot be really implemented. It becomes much harder to visualize. So what you want is to have software to find the values of theta 0 and other parameters. And in the next slides, we'll start to talk about an algorithm for automatically finding that value of theta 0 and theta 1, etc., that minimizes the cost function. We previously defined the cost function j. In this slide, I want to tell you about an algorithm called gradient descent for minimizing the cost function j. It turns out that gradient descent is a more general algorithm and is used not only in linear regression, it is actually used all over the place in machine learning. And later in the class, we will use gradient descent to minimize other functions as well, not just the cost function j for linear regression. So in this slide, I am going to talk about gradient descent for minimizing some arbitrary function j. And in the later lectures, we will talk those algorithms and apply it specially to the cost function j that we had defined for linear regression. So here is the problem setup. We are going to assume that we have some function j of theta 0, theta 1, maybe as a cost function from linear regression, or maybe it is some other function we want to minimize. And we want to come over algorithm for minimizing that as a function of j of theta 0 and theta 1. It turns out that gradient descent actually applies to more general functions. So imagine if you have a function that is a function of j of theta 0, theta 1, theta 2 up to theta n, and you want to minimize over theta 0 up to theta n for this j. But for the sake of simplicity, I'm just going to assume that I have only two parameters throughout the rest of this lecture. Here is the idea for gradient descent. We are going to start off with some initial guesses for theta 0 and theta 1, and it doesn't matter what the values are. What we are going to do in gradient descent is we will keep changing theta 0 and theta 1 a little bit. Then try to reduce j until hopefully we end up to a minimum value. Let us say I want to go downhill as quickly as possible. What direction do I take when I take little baby step? If I want to physically walk down this hill as rapidly as possible, how will I do it? If you are standing at the initial point shown in the slide and you look around, you will find that the best direction to take a little step downhill is roughly in this direction. And now you have a new point. You are going to again look around and then find what direction should you step in order to take a little baby step downhill. So if you take another step in that direction, then you keep going from the new point, you look around, decide what direction will you take downhill most quickly. Take another step, then another step, then another step, and so on. And finally, you will end up to a local minimum point, which is marked as a white star. Now let us imagine that we have initialized gradient descent just a couple of steps to the right. If you had to repeat the process, so stop at that point, look all around, and take a little step. And you would do that, then look around and take another step, and so on. And if you started just a couple of steps, the gradient descent would have taken you the next local minima. So the second white star indicates the second local minima. So if you started just at a little bit slightly different location, you would have end up at a different local minima. And that is the intuition in picture for gradient descent. Let us look at this slide. This is the definition of gradient descent algorithm. We are going to just repeat the loop until converging. So we are going to update the parameters theta j by taking theta j and subtracting from it alpha times a term. So let us see a lot of details in this equation. So let me discuss some of it. First, this notation here, colon equals, to denote assignment. So it is an assignment operator. So concretely, if I write A colon equals B, what this means is it's an assignment statement. Whereas in contrast, if I use the equal sign, then I write A equals B. Then it is a truth assertion. I am asserting that the value of A equals to value of B. I am just making a claim that the value of A and B are the same. I won't write A equals A plus 1 because this is wrong. Next, the alpha in the equation. This alpha here is a number that is called learning rate. And what alpha does? It basically controls how big a step will be. We take downhill with creating descent. So if alpha is very large, then that corresponds to a very aggressive gradient descent. When we are trying to take huge steps downhill, and if alpha is very small, then we are taking little baby steps downhill. And I will come back and say more about this later about how to set alpha and so on. Finally, the term here, which is derivative term. I do not want to talk about it right now, but I will derive this derivative term later and tell you exactly what that is. The last point is you want to simultaneously update theta 0 and theta 1. And this is a correct implementation of simultaneous update. The theta 0 and theta 1, the new values, are taken into temporary variable temp0 and temp1, and finally the theta0 and theta1 are replaced by those temp0 and temp1. And if you see the incorrect implementation, here is the incorrect implementation that does not do a simultaneous update, because you have now plugged in new values of theta0 into the next equation. When people talk about gradient descent, they always mean simultaneous update. We are going to go into the details of the derivative term, and we'll let you know everything you need to compute that derivative term. In the previous slide, we gave a mathematical definition of gradient descent. In this slide, we'll get better intuition about what the algorithm is doing and why the steps of gradient descent algorithm might make sense. Here is the gradient descent algorithm that we saw last time. And I just remind you the term alpha in the equation, this alpha, is called the learning rate. And the term adjacent to the alpha is the derivative term, the derivative of j with respect to theta j. So let us use a slightly simpler example where we want to minimize a function of just one parameter. So we have a cost function j of just one parameter, theta1, like we did a few slides back, when the theta1 is a real number. So just again we can have 1D plot. So in the plot, you see this point is the initial point, and if I find the derivative at that point, derivative of j at that point, that means the slope of this point, you can see the slope is a positive slope. So in the formula of updating formula, theta j equal to theta j minus alpha multiplied by a positive number. What does it mean? It means theta1 will be decreasing because you are subtracting a positive number from previous theta. On the other hand, if you take the another example where the initial point is at that point, that means at the point over there, and if you take the slope at that point, the slope is actually negative slope, which is the derivative of j at that point. So if I apply in that same formula, we end up with theta1 minus alpha and negative number. So it means theta1 will be increasing because you are adding something with theta1. That's why it will advancing toward the minimum point. In the previous case also, the theta is decreasing. It means it is advancing to the minimum point. And in this example, when theta is increasing, it is also advancing towards minimum point. So in both the example, we can see that the algorithm will be forcing the theta, updated theta, toward the minimum point. So let us now discuss about the effect of alpha, learning rate, in convergence. Here is the formula for theta0 equal to 0, theta1 equal to theta1 minus alpha times derivative of cost function j. So first of all, let us discuss what happens if alpha is too small. When alpha is too small, gradient descent can be very slow. Let us see by an example. Here is the curve for j with respect to theta1. And let us start at this point, they marked in red, and this point is the starting point. And if alpha is very slow, when it calculates the derivative at that point, that means tangent at that point, then if you multiply that derivative term with a small alpha, it will end up with a small step. The step will be very small, we call it baby step. And if you go further, there will be another baby step, and so it will advance in this manner. On the other hand, if alpha is too large, then gradient descent can overshoot the minimum. It may fail to converge, or even it may diverge. So let us see that by another example. If you start at a point and you find the slope at that point, or derivative of the function j at the initial point marked by a red point, so and if you apply or you multiply that derivative with a large value of alpha, you may end up with that point, new point. And if you start finding the gradient at that point, that means derivative at that point, and if you multiply again by a big number, since it is a positive slope at that point, and if you now multiply by a large value of alpha, you may end up with a point over there. So similarly, if you find now the slope and multiply a large value of alpha, it may end up with another point in the positive side. So if you continue multiplying with a large number with the derivative, then you may actually diverge from the minimum point, where we are expecting that it will converge towards minimum point. Well, but because alpha is too large, the gradient descent algorithm will not converge in this case. Let us discuss what happens if initial value of theta 1 is at local minimum. You see in this diagram, the variation of j with respect to theta 1 is such there are several minimum, and we call them local minimum. And if I initialize our program at that level where the theta 1 is a value which corresponds to a local minimum of the curve. So what happens if I calculate the slope at that point? I will find the slope is 0 because the tangent will be horizontal. And if we put that value of slope into the derivative, that means the subtracting term will be 0. So theta 1 will remain as theta 1. It means the theta 1 will not be updated. And this case happens when we do the regular convergence program. That means the program when converging towards minimum point, at certain point it reaches the minimum point, minimum value. So the theta 1 will not update at that point. But in practice, will not get always exactly 0. That means the slope will be in computer calculation will be something like 0.0001 or less than that. So we have to limit the value of slope or value of updating term to end our iteration. So iteration will be stopped at certain value of theta 1 updating quantity. That means this quantity will determine where we will stop the iteration. Sometimes it appears to us that in order to have convergence, we may have to reduce the value of alpha as it progresses towards minimum value, because it may appear that the alpha value may cause the divergence. So intuition says us that alpha should be reduced when it is moving towards minimum value. But this slide will show you even alpha is fixed, it can converge. So gradient descent can converge to a local minima even with alpha rate is fixed. So you see the formula for updating theta 1, and this is the curve of j with respect to theta 1. And let us say we have initialized our program at that point, and you see the slope. Slope is a steep slope, So value of slope is very high. So if I multiply that slope with alpha, then it will be a certain quantity. But if I progress, the next point could be this point, and then you can see the slope here is less than the previous one. That means if you keep the alpha fixed, the term that is adding with the theta 1 or subtracting with the theta 1 in this case will be actually reduced because the slope has reduced. Similarly, if I proceed further, the slope has decreased a little bit more. The slope S3 is less than S2. So the subtracting term has again reduced. That means as you progress towards minimum point, the term which we are subtracting is reducing gradually, even alpha is fixed. As we approach to local minima, gradient descent will automatically take smaller steps. So no need to decrease alpha. Let us now discuss about the complete linear regression model. We develop gradient descent algorithm, which is shown on the left side. The repeat until convergence, update theta j with theta j minus alpha multiplied by derivative of j theta, where theta are theta 0 and theta 1. So partial derivative means you have to derive the derivative of j with respect to theta 0 and again with respect to theta 1. And we discussed about the linear regression model where hx hypothesis is equal to theta 0 plus theta 1x, and the cost function, we define cost function as average of square error, where error is defined by the hypothesis minus y for different data set. So you take the square of the errors and sum them together, I varying from 1 to m, and then take an average 1 over 2m. And you remember 1 over 2 is out of the average, but this is kept to make some formulation easier. You see the derivation here where j theta is given by this function and this j theta is put in the derivative function. So now we have to find out the derivative of this third bracket quantity or third bracket expression, first with respect to theta 0 and then with respect to theta 1. So if I develop the equation for different theta, that means theta 0 and theta 1, I have to actually make the derivative of this equation where h has been replaced by theta 0 plus theta 1x. If I take the derivative for theta 0, that means when j equal to 0, then it comes out to be this equation. Because if you derive the first derivative of this equation, the 2 in the power will come in the front and the multiplying factor will be equal to 1 by m. And since you are taking derivative with respect to theta 0 and theta 0 is a free quantity, so if you just take the derivative of this term, it will be multiplied by 1. But in case of j equal to 1, when you are making derivative with respect to theta 1, then the same thing you are doing, that means the 2 in the power will come in the front, so 1 over m, but now you are taking derivative with respect to theta 1, so the term xi will appear as a multiplication term. So this is equation for theta 0 with respect to theta 0, and this is equation for j, derivative of j with respect to theta 1. So this is our complete equation, and you have to put the h of x theta 0 plus theta 1x in the place of h theta xi, and you have to do the updating simultaneously. We talked about what is meant by simultaneous update and what is meant by non-simultaneous update. So you have to make use of that knowledge to make the simultaneous update for our model. This is a diagram for cost function for linear regression, and this is a convex like or bowl shape like function, and you see the bottom of the surface is the minimum point, and this shape is unique for linear regression. If we follow the gradient descent algorithm, if we relate the convergence with the contour map, that means how convergence occurs. If you want to visualize in the contour map with respect to hypothesis function, as hypothesis function changes, how the point in the contour changes. If we discuss that one, we can easily see that as it converges towards the minimum error hypothesis, and in the contour map we will see the point also converges towards minimum point. So in the figure, this line is the initial hypothesis, and you can see this is not a good fit, the points over there, and that's why if you calculate error or the cost function, it will appear in this ellipse. This ellipse is for certain cost function. So the value there is for certain theta 0 and certain theta 1. So the theta 0 here is about 800, and theta 1 is slope of this line. So if I make another straight line which is a bit different from the previous one, and it is closer to the points, that means it is better than the previous one, you can see the movement in the contour line. The point now in the contour line is different from the previous one, and you can remember the minimum point is the center of the ellipse. So this is the minimum point, and the movement of the contour point as we progress with the different hypothesis, that means different theta 0 and theta 1, it is moving towards that line. So if I take another line which is flat line, of course it's better than the previous two, so it has moved again to another point in the contour plane, and it is heading towards the minimum point. If I progress similarly with the other line, you can see the progress in the contour map, and the point, the red crosses, is moving to the minimum point. And maybe this is the lowest error line or having minimum cost function, and the red cross is at the center. As we move the hypothesis by changing theta 0 and theta 1, and this is automatically done by the gradient descent algorithm. As we apply the gradient descent algorithm, the straight line will move from our initial straight line towards the best straight line or best hypothesis. Let's talk about 2 points. One is batch gradient descent, other is numerical method without iterations. The method that we follow is batch gradient descent. It is called batch because we are using all the data in our calculations. That means each step of gradient descent uses all the training example. You can see from I equal to 0 to m. That means all data set, given data set, has been used in finding the cost function. There are methods where not all data sets are used, rather portion of data sets are used in the algorithm. They are called non-batch methods. We'll discuss about non-batch method later on. In some technique, non-batch method is essential and we'll of course discuss at that point of lecture. Numerical method without iterations. The method that we followed needs iteration. At every iteration, we change theta 0 and theta 1, and at certain point of time, we'll end up with a result. At certain point of time, we end up with a minimum error point. Let us discuss about numerical method without iterations. There is numerical method by which the formula for finding theta 0 can be established. And the least square method, if we follow the least square method, then the theta 0 and theta 1, the formula for theta 0 and theta 1 can be found out. And thetas can be calculated from that set of formula. No iteration is needed there. In our case, we use iterative method, and every time we change theta 0 and theta 1 following gradient descent. But gradient descent algorithm works better than this technique of numerical methods. So direct equation is one technique, and numerical methods is another technique of finding or updating theta 0 and theta 1. We'll discuss our direct method at some point of our lecture, but normally we'll use iterative method in gradient descent algorithm. Let us discuss about a larger number of features. In the examples that we discussed so far, consider just single feature X. In case of housing problem, the size of the house, the square feet, was the single feature, and cost is the value of Y, which is the output of the housing problem. You see the problem with only one feature, that X, the different X values was given, and the price in lakh of taka is given as a Y value. But instead of just only size, the feature can be many, like number of bedroom, number of floors, age of the homes. That may also affect the price. That's why instead of single X, there could be X1, X2, X3, X4, etc. So the Y value depends on all the features. Maybe the degree of involvement of the features may be different. One may affect more than the other. But there may be some relationship with the other features and other than the only size. So if we have to consider the number of features which is not singular, how to incorporate in the formula? Instead of x, we have to write, for example, x1 theta 1, x2 theta 2, x3 theta 3, x4 theta 4, etc. So the same hypothesis function h of x. Now instead of writing theta 0 plus theta 1 x, we'll write theta 0 plus theta 1 x1, theta 2 x2 up to theta 2, theta 4 x4. So this is the extension of the previous discussion. In the previous example, we have seen multivariable housing problem. The number of variable, for example, was size of the house, number of bedroom, number of floors, and age of the home. And those four elements are called features. Previously, we considered single feature. Now we have a multiple feature. So if we have number of data set, so total number of feature will be number of data set multiplied by number of features. So we can represent all this data only related to features in a matrix. The rows in the matrix represents the data set, and the column in the matrix represents the features. For example, this column is a feature, this column another feature, number of bedrooms, this column number of floors, and the fourth column is number of ages or age of the homes. And the rows each row represent the individual data sets. So for certain data set, we have first row, second row, third row, fourth row. So similarly, in case of Y, that means the price of the houses, which are singular, but for different data set, there are different values. So those can be combined together in another matrix. Since this is a single column matrix, that's why it is called vector. So these two representation makes the equation easier. All the calculation will follow later on. We see if the representation is in matrix or vector form, then the calculations becomes easier. That's why we have to have basic knowledge about linear algebra related to matrix and vector manipulation. So in the next slide, we'll discuss about some very fundamental linear algebra related to matrix and vector. Most of those points are actually known to you because you have already covered those topics in your undergraduate program. Now let us discuss some fundamental points of linear algebra related to matrix and vector. First of all, you have noticed the difference between matrix and vector. A matrix is a two-dimensional array like this one, A equal to A11, A12, A13, etc. So these are two-dimensional, row and column, both are present. In case of vector, it's a single dimensional column matrix. You can call this also matrix, but normally when it is a single column, then we call it vector. Then dimension of matrix and vector. Dimension of a matrix is said to be m by n matrix, where m is the number of row, n is the number of column. For example, in case of A, it is a 3 by 4 matrix. In case of vector, the number of rows in the single column determines the dimension of the vector. For example, the vector B will be called three-dimensional vector. So let us continue discussing some fundamentals of linear algebra, zero index and one index matrix vector. Sometimes the index starts from 0 and sometimes index starts from 1. If the numbering of the rows column starts from 0, that means 0, 1, 2, 3, etc., then it is called zero index matrix or vector. Like this vector is a zero index, x0, x1, x2. The numbering, if it starts from 1, then it is called one index. The rules of addition and subtraction. The addition and subtraction can only be performed between two matrices or vector of same dimension. If the dimensions are not same, you cannot add or subtract. The dimension of the resultant matrix or vector is of same dimension. So let's continue. Scalar multiplication or division. If a matrix or vector is pre or post multiplied by a scalar number, just a number, all elements of the matrix vector are multiplied by the scalar number. For example, A is matrix like this. It's a 3 by 4 matrix. And if you multiply the A matrix with 4.5, what will be the B matrix? So B matrix will be all elements will be multiplied by 4.5. For example, 4.5 A11, 4.5 A12, etc. And it is applied for post multiplication also. A multiplied by 4.5 is same as 4.5 multiplied by A. This is applicable for scalar multiplication. Post and pre are same. Rules of multiplication. One matrix or vector A can only be multiplied with another matrix or vector B only when the number of column of A is equal to number of rows in B. For example, A and B are multiplied and C is the result. So the dimension of A is m by k and dimension of B is k by n. You notice that k is same in both cases. What is the k? K is the number of column in A matrix and k is number of rows in B matrix. So the number of columns in A and number of rows in B has to be same. Otherwise multiplication will not happen. And the resultant dimension will be m by n. So you can remember by this that the k will be dropped. So the number of rows of A matrix and number of column in the B matrix will be the number of rows and columns in the C matrix. So how to do the multiplication? This is given by this formula Cij equal to P starting from 1 to K A IP multiplied by B Pi. This is a summation. A row is taken from A and a column is taken from B and all the elements are multiplied. Since the number of elements are same in the two cases, so you can sum them together and obtain a result. We'll see an example later on. So I is varying from 1 to m and j will be varying from 1 to n. So multiplication in housing price calculation. In this illustration, we will see the application of multiplication, matrix multiplication. If the hypothesis is hx equal to 100 plus 0.3x, calculate the house prices for house areas of 2100, 1560, 1200, square feet. Use matrix multiplication. So the result will be like this. Let us form a row matrix with the elements in the H, that means hypothesis, 100 and 0.03, and the square feet, that means the area, are arranged in a second matrix. 1 is the first row and the areas in the second row. Why we have arranged in this way? If you multiply these two matrices, you will get the prices for different square feet. For example, in this case, 100 and 0.03, this row will be multiplied with this column. So 100 multiplied by 1 plus 0.3 multiplied by 2100. Similarly, for this column, 100 multiplied by 1 and 0.3 multiplied by 1560. Similarly, others. So you will get 4 elements of cost or prices if you multiply these two matrices. And the elements of the prices will be arranged in a vector form, that means in a column. So every element in the column represents the price corresponding to that particular square feet. Now let us discuss about identity matrix. Identity matrix is a square matrix whose diagonal elements are 1 and all other elements are 0. For example, I matrix here is identity matrix. This is a 3 by 3 matrix. So 3-dimensional identity matrix, because the diagonals are 1 and all other elements of diagonal elements are 0. Inverse of a matrix. A matrix B is said to be an inverse of A when A multiplied by B is I matrix. So in order to multiply B matrix, you have to take inverse. Normally, we will take help of the different routines available in the different programs. So we are not going into fundamental of how to calculate the inverse. Transpose of a matrix. When a matrix is transposed, the row of the matrix becomes column and vice versa. For example, A is shown here and A transpose is also shown. You can see the row in the first case becomes the column in the second case. So in this way, you can make the transpose. All the discussion we made on the fundamentals are very few. There are lots of discussion will be going on during our different lectures related to linear algebra, and when we discuss different algorithms. So that's all for the lecture 2. Thanks.